My name is Jingshui Huang. Today I'm going to present to you our study on the topic of river water quality and extreme summer low flow, which I did in Helmholtz Center for Environmental Research, UFZ, together with Professor Dietrich Burschert and Michael Rohde earlier of this year. The title of the study is High-Frequency Sensor Measurements Supported Modeling In-Stream Nitrogen Uptake at Extreme Summer Low Flow. Experience draws from 3 years since 2018, which led to summer extreme low flow in the water bodies. And a climate change, summer drought is likely to be more frequent and intense in Central Europe. Extreme summer low flow has not only consequences on water quantity, but also cascading effects on water quality. Our aim of the study is to investigate the river water quality and nitrogen uptake in the recent extreme summer low flow period in central Germany using high-frequency water quality data and combined with the modeling method. To reach this goal, we chose the 27-kilometer six-order agricultural stream Lower Boulder in Saxony-Anhalt in Germany as our study reach, which experienced extreme summer low flow in 2018. In this stretch, there are 2 discharge gauging stations and 2 water quality probes installed, one near upstream at Catchments GGL and one near downstream at Schlossfoot STF. We chose July and August 2018 as extreme summer low flow condition, which has the median discharge value lower than 1 percentile, to compare with the July and August in 2017 as the normal low flow, which has the median daily discharge value lower than 10 percentile, which We obtain water temperature, oxygen, nitrogen, and chlorophyll A concentration at both stations at 15 minutes interval. We estimated stream metabolic rates, including gross primary productivity, community respiration, and net ecosystem productivity using single station method with the high-frequency oxygen data. In order to estimate the nitrogen uptake metrics continuously, we used WASP advanced eutrophication module to set up a water quality model for the Lower Boulder domain for 5 years. We calibrate the model by comparing the goodness of the fit of 15 minutes interval simulations versus observations at Schlossfoot. Based on model result, we calculate nitrogen uptake metrics, including aerial nitrogen gross uptake rate, aerial nitrogen net uptake rate, net up velocity, and length at daily scale. Besides, we also can differentiate the aerial net uptake rate into the nitrification rate and net uptake rate by phytoplankton and benthic algae. Finally, compare the physio-chemical variables, diurnal oxygen indexes, stream metabolisms, uptake rate, and pathways in the summer extreme low flow condition and the normal low flow condition by conducting Cruz-Valles test. The results of physiochemical variables from the high-frequency measurements at both stations. We found out that water temperature was significantly higher at extreme summer low flow. The median value were more than 1 degree Celsius higher than those in normal low flow conditions. The nitrate concentration were significantly lower at both stations at extreme low flow conditions. It could be explained by the reduced catchment to stream connection and thereby reduced input loadings. The possible enhancement of in-stream processing could be another reason for the lower concentration. We found out that oxygen concentration in both stations were significantly lower. This could be related to the reduced solubility caused by the increased water temperature. And chlorophyll A concentration was significantly lower at Catchments, and while the concentration was significantly higher at Schlossfoot. The difference in the chlorophyll A concentration between the 2 stations has a small but significant increase, which means phytoplankton accumulated more in this range at extreme summer low flow condition. This is probably due to the increase increased residence time at summer extreme low flow condition. However, when we have a look at the high frequency data during the summer low flow period, they usually have a very obvious diurnal pattern. Therefore, we will not only look at values as a whole, but also look at the diurnal oxygen indexes. We identified the daily maximum, minimum, mean, and the delta, which is defined as the by the difference between maximum and minimum. The Kruskalvali's test results showed us that the daily oxygen maximum at Kosovo sleep is significantly higher at extreme low flow. In contrast, the oxygen minimum or at both stations are significantly lower. Therefore, the daily oxygen deltas are significantly larger in both stations, which implied a higher primary productivity in the range. The stream metabolic rates calculated by the single station method showed us that the aerial gross primary productivity rate indeed increased significantly at summer extreme low flow. Simultaneously, the community respiration rate also increased significantly. However, the increase of the gross primary productivity was higher than community respiration. As a result, net ecosystem productivity is closer to zero. The system was still most of the time heterotrophic at extreme summer low flow conditions like the normal ones, but less heterotrophic than in the normal conditions. At summer extreme low flow condition, although the accumulation of phytoplankton in this range increased, as the absolute level of the phytoplankton is still in the lower range with the median value of chlorophyll less than 6 milligram per liter, the contribution to the increase of gross primary productivity is still limited. Therefore, we can expect the increase of gross primary productivity mostly by benthic algae. In addition, higher gross primary productivity at summer extreme low flow also implied the elevated gross asymmetry nutrient uptake rate. But before compared the nitrogen uptake matrix results, we first calibrate the model performance for 5 years. Our simulation results of discharge, nitrate, oxygen, chlorophyll A showed a good model performance for the 5 years period. Based on the model results, we could compare the daily aerial gross uptake rate and aerial net uptake rate, velocity and length, and percentage uptake. Kruskalvali's test results showed us that the gross uptake rate is significantly higher at summer extreme low flow than the normal low flow in the lower border. The median of the gross uptake rate at extreme low flow has increased 26%. However, the net uptake rate is not significantly different at extreme summer low flow than the normal low flow. The median of the net uptake increased 30%. The different response of gross uptake and net uptake at summer extreme low flow implied that the enhancement of the internal processing of the nutrients. Besides, velocity has been increased and the spiral length has decreased significantly at extreme summer low flow, which implied the system became more efficient in processing nitrogen. The uptake efficiencies has been also significantly increased by more than 2-fold, which is an effect of both enhanced processing and decreased input loadings. Regarding pathways, we found out that the denitrification rate is not significantly different at extreme semi-low flow than in normal ones. When on the one hand, denitrification could be enhanced by temperature increase, but on the other hand, the nitrate concentration decreased significantly. In addition, slightly lowered oxygen is also not enough to create more favorable redox condition for denitrification. Therefore, aerial denitrification rates were not significantly different at summer extreme low flow than the normal ones. In contrast, the net assimilatory uptake by benthic algae and phytoplankton both increased. The assimilatory uptake by benthic algae has significantly increased by 30% at summer extreme low flow than normal ones, whereas the assimilatory uptake by phytoplankton increased slightly, about 6%, and also insignificantly. This could be explained by the taxonomic compositions of phytoplankton and benthic algae in the lower border. Taxonomic compositions of the phytoplankton were identified as being dominated by diatoms in the lower border, which has their optimal growth temperature at 13 to 14 degrees Celsius. Therefore, under the extreme summer low flow conditions, the increased water temperature was not a boost for its development, although the longer residence time at extreme low flow has a positive effect for the phytoplankton development. In contrast, the taxonomy investigation showed that the dominant species of macrophytes in the lower border was Phytomorgitum pectinus, which has the maximum net photosynthesis with the optimal temperature of 30 degrees Celsius. Therefore, higher temperature at the extreme summer low flow condition could enhance their productivity and thereby nitrogen assimilation. However, we should notice that the median water temperature increased only 1 degree Celsius at summer extreme low flow. It will create a 30% boost of the uptake. Since the system is not nutrient limited as well, we suggest increased light availability and summer extreme low flow could be a great stimulator for the primary productivity for the benthic algae, which could be supported by the conclusion of a recent study that a decrease of turbidity below 10 still increase gross primary productivity under the drought condition. Finally, we would like to summarize what we have learned from the water quality and processes under summer extreme low flow condition in 2018 in the lower border. Lower border is a typical agricultural lower-land stream. At extreme summer low flow in 2018, the water temperature became higher. As a consequence, the average oxygen concentrations decreased. However, the diurnal delta of oxygen concentrations increased significantly, which is a hint of the metabolism change in the system. Indeed, both the primary productivity and community respiration rate were significantly enhanced at extreme summer low flow condition. However, the enhancement of gross primary productivity is higher than the community respiration, which means the system turned less heterotrophic. The elevated light availability is likely to account for enhanced gross primary productivity in the system. At extreme summer low flow, the system metabolism remained dominated by the benthic algae, although the phytoplankton chlorophyll A concentration increased significantly. It still remained a low level, and the benthic algae biomasses increased to a higher magnitude. Regarding nitrogen, the nitrate concentration was lower at extreme summer low flow because the reduced connection with the catchment and higher efficiency in processing nitrogen in the stream system. Besides, during the extreme summer low flow, the internal recycling of nitrogen has also been enhanced. The only nitrogen processing pathway which has significantly enhancement of the uptake rate is the a simulation by the Uptake algae. The nitrification rate and uptake rate by phytoplankton did not change significantly at summer extreme low flow conditions. In this case, we learned that many of the state variables and the processes in the system were changed and responded significantly in extreme summer low flow period in the lower border in 2018. However, the changes seems not to become significant enough to cause a large and more important system change. In the future scenarios of more severe extreme summer low flow, discharge could be even lower, temperature will get even higher, rest time even longer, volume and depth even smaller. Then what could be happen under these scenarios? We should ask ourselves if the oxygen minimum value in the night would be below the threshold of the health ecosystem standard, if the system will become autotrophic because of the further enhanced growth primary productivity, if the phytoplankton community will have succession from diatom, which likes lower temperature, to more high temperature tolerant phytoplanktons, for example, cyanobacteria, and also if the system happen regime shift from benthic algae dominated to phytoplankton dominated one, if the phytoplankton bloom and it happened hypoxia and it excreted a lot of toxin, these all will cause catastrophic consequences on our ecosystem and also safe drinking water supply and human recreation activities. With these open questions, I will end my today's presentation. Thanks a lot for your attention. Now I'm happy to take questions from you.